Okay, so what I want to do is I'm not a huge fan of PowerPoint slides, but they do serve a purpose to a certain extent. They're going to allow us to kind of understand the idea of optimization. And then I want to devote the majority of the time to actually doing a live presentation or a live demonstration as to how to go about running an analysis or running an optimization. But to kind of give you the background, the understanding of what optimization is, it's best served to look at slides here. So optimization, to find the best compromise among several often conflicting requirements, as in engineering design, a mathematical technique for finding a maximum or minimum value of a function, selection of the best element with regard to some set of elements. So we get the technical terms, the dictionary definition of optimization. But in a more understandable way, optimization is taking and coming up with an engineering design that is the best use of material, the minimum amount of material necessary to accomplish what you're looking to do, with, of course, with appropriate safety buffers built in. But utilize the minimum amount of material to make the part more economical to build, to make the part lighter weight, and in some cases, even stronger than the non-optimized design. The typical design process is you create a design, you analyze it, you evaluate it, you take a look at the factors, you do an update, you return to analysis, and you go through this whole cycle, this iterative cycle of design, analysis, review, design, analysis, review. If instead you approach the design process with optimization in the core design process, what it's going to allow you to do is develop far more intelligent simulation-driven designs quicker and remove that entire iterative process. Maybe go through a few iterations in the optimization, but most of that is to come up with a concept design and then refine it. What optimization allows us to do is it's not necessarily going to design the part for us, but in a classical example of the design process, if along this axis we have time, we can see here at the very beginning of the design process, we have, with this orange curve here, the minimum amount of product knowledge that we're going to have through the entire design process. We know the least amount of our product. But contradictory area, unfortunately, at the point that we have the least amount of knowledge, we actually have the most design freedom we will have in the entire process. And so that limits our ability to create a good design because we don't know enough about the design yet. And as we move further and further along, you can see we gain product knowledge, but that comes at the expense of design freedom. We don't have the freedom to change the part as we'd like to. So the idea of optimization is actually to shift this orange curve to kind of this red dotted curve and acquire much more information about our part while we still have the most freedom possible to affect the design. And I'm going to skip through a number of these because I want to get to this right here. So an example of what optimization is. This is just kind of a thought experiment here. We're going to start with a cantilever beam. It's going to be modeled with 1D elements, and this is what the physical representation of that would be. So we just have a cantilever beam. We have a length, we have a height, and we have a base width right here. That's going to be loaded with a force of 2,400 newtons. The width and the height of the cross section are what's going to be optimized. So we're going to change these two values here, and we're going to alter them to get the best design that has the minimal amount of weight. But of course, if that were all we were doing, it would just shrink down to an incredibly thin little part, and that would be the minimum amount of weight. So what we do instead to prevent that from happening is we have to set some sort of limit on it, and the limit on that is that the normal and shear stresses can't exceed the yield. Obviously, we don't want the part to bend. Also, we're just as a design to make sure we end up with a design we like, the height of the part should not be larger than twice the width of the B. So this is kind of the word explanation of what we're going to be doing with an optimization. Now, when we kind of put that into numbers, you can see we have these things here called design variables. And the design variables across, and we're going to come back to these terms right here. The design variable is a cross section of the beam. So the width of the beam, the lower to the upper, and if we define that, we can say that we want to go from 20 to 40. So that's our width limit. We can't have a beam that's smaller than 20. We can't have a beam that's wider than 40. And the height, we're going to bound by 30 to 90. The responses, the things that the information that we're getting from our design when it goes through the optimization are the normal stress, the shear stress, and the overall mass of the part. The constraints we're going to set on the optimization, the two stresses where the maximum is 160, probably megapascals, and 60 megapascals. And then the objective is a weight, and that weight is going to be minimized as a function of the base and the height. So that's now kind of putting numbers to the idea of the optimization. Now this is where we see what the optimization is really about. If we take a look at this, each one of these different lines here represents a possible combination of width and height that results in the same amount of stress. So each one of these is a different combination for the same amount of stress. And if we start eliminating regions of this based upon our requirements, so you can see stress limit maximum of 160. So anything above that line becomes infeasible because that would exceed that stress limit. Anything above this line, which is entirely within this, so all we focus on is this stress. And then these bounding lines right here represent the overall dimensions of the part. So between 30 and 90 for the height, between 20 and 40 for the width. And then this blue line coming up here is going to represent a combination that results in heights less than 2 times the width, so everything below that. And by cutting away all of this, we get rid of all of this kind of pink area here, and we end up with just this little green triangle of what we call a feasible domain. So everything that falls within this little green triangle, bound on this side by the overall maximum beam width, bound on the bottom by the curve that represents that maximum stress, bound on the top by the line that represents the height being less than or equal to twice the base. That little green area, every single possible combination of width and height that fall within this are our feasible domain. So if I were to say pick 37 millimeters for the width and 65 millimeters for the height, that would fall right there, and that would be an acceptable design. But we don't just want acceptable design, we want the optimized design. And if we look at this domain here, right down at the corner where this black dot is, where we're at about 22.5 millimeters for the width and 45 millimeters for the height, that is our optimized design, because each one of these going down is a lighter weight part. So that is the lightest possible part as a function of the width and the height that falls within the feasible domain. That's how optimization works. We set our requirements. We limit the results to exclude things that don't meet our requirement. And then within the all of the possible feasible domains, the optimizer choices in the feasible domain, the optimization solver is going to pick the one that is, in this case, the least that falls within there. And that, at its core, is what optimization is. So a little bit about terminology, because we're going to be using these terms quite often through this entire session here. Design variables, these are the parameters that can be changed. So thinking back to our cantilever beam, the two things that we could change on that are the beam width and the beam height. Those are the two things we change. So if we're optimizing something, something has to be able to be changed, whether it's a dimension, whether an element exists or not, the size of something, the diameter of something, the thickness of a material. Something has to be able to be changed, and that's what we define as our design variable. The design space is the limits to those design variables, how far we can go with those variables. Responses are the things that we have to keep track of. So what is important to this optimization? If I'm looking to optimize a cantilever beam and I want to minimize the mass, I'm not going to care about the displacement of some random point or node in the middle of the part. Responses are the things that we care about. In this case, the two stresses and the mass. Constraints are limits on those. And then an objective is what our ultimate goal is. Usually it's or not usually, it takes one of the responses and sets a limit on it. Feasible design is one that satisfies all of our constraints, doesn't violate anything. Infeasible design is a design that violates one or possibly more of the constraints. And then the optimum design is the set of variables along with the minimize or maximize objective that satisfy all the constraints. So in that case, the little black dot. When we're done with the optimization, there are some questions that we typically have to ask ourselves. First of all, did we reach our objective? Was the goal that we set reached? And how much did the objective improve? And that's important. There are times where we will run an optimization on something and find out that it did not improve, it improved the overall design, but it didn't improve it enough to warrant the time or expense of changing the current design. If I come up with an optimized design on a control arm and the part only ends up being a half an ounce less mass, is it going to be worth the hundreds of thousands of dollars I have to put into changing the tools, the time down because the tools are being changed to get just that half an ounce savings? But if it turns out that I'm going to remove 3 pounds out of the mass of the control arm, and over that time, that means that I'm going to get better fuel efficiency with my vehicle. I can create the part cheaper. Then heck yeah, it's worth the change. What are the design variables? What exactly is the result of the optimization? What is the shape? What is the size? What is the dimension? What is the material type? All of the different things that I was studying. What are they, so that I know how to incorporate it into my design change? Constraints. Did we violate any of the constraints? And oftentimes we will. And if that's the case, if we violated a constraint, sometimes it's worth taking a look at that and determining, was that constraint really important, or did we put too tight of a constraint on there? We can get this information from some files in the analysis, the out file, and then the MVW file that we can view in HyperView. Some issues that we can encounter: local versus global, extreme, a maximum or minima. So this is a local maxima when actually the global maximum is up here, or a local minimum versus a global minimum. Did we over-constrain our part? There are times when an optimization can just not work at all. Did we over-constrain it, or perhaps under-constrain it? An example of that, when many years ago we had an application engineer who was just starting out and was on his first project working with a customer doing an optimization. And he contacts me late in the evening in a bit of a panic because he's got to present some optimization results the next day. And he is running the optimization, and when he takes a look at the result, the entire part of his design space has just been completely eliminated. It's all gone. He doesn't know what's going on. So we take a quick look at his thing, and it turns out he under-constrained the model. He needed to set a limit as to how much could be removed. It optimized it. It got rid of everything. It made it as light as possible. So mistakes like that can come up, and we need to take a look at those. And then finally, issues related to FE modeling. It is critically important that you have a good, reliable, well-meshed part to make sure that you get a good optimization. We have many different types of optimization in our software. Topology, which is what we're going to cover today, is far and away the most commonly used one, and we'll get more in depth into a discussion about topology. These are what we call concept level designs. So this is where we don't entirely know what our part is going to look like, and this is going to help us better understand the overall size, shape, material distribution of our part. Free size is similar to topology in that, but it only works on shell elements. And it's going to vary the thickness of elements. It's great for composite optimization. Topography is a way of taking shells and adding beads to the part to stiffen it. Then we move on to what's called fine-tuning techniques. So once I have an idea of what my part should look like, now I can fine-tune it. Parameter and size is going to find the optimum component thickness of a part. Shape allows me to change things like this flat area or a radius, fine-tune those. And then free shape is another way of altering the overall shape. So we're no longer affecting the total overall size of the part or shape of the part. We're changing local areas. So you can kind of see the overall pattern here, the path that we take. We start with a design space, a big block of material. We mesh it, we run an analysis on it, make sure that it can be run. We do our topological optimization where it gets rid of unnecessary materials. We perhaps fine-tune that to change the shapes of some of the radii, do some fine-tuning. You can see these two designs, very similar. We're not making drastic changes, but just kind of more local changes. And then finally, taking the optimized shape and coming up with the final design. Let me go to the next slide here. I promise you we're almost done with the slides. Just going to work out better if we cover this idea here before we kind of get into the definitions here. And There we go. So the last thing I want to talk about is what we call the Drco approach. So what is the Drco? And that's the kind of the nifty thing about optimization is if you follow this pattern, if you follow this approach, optimizations are surprisingly easy to do. So Drco, the D stands for design variable. So this is the order in which you're going to define things. The first thing we're going to do is establish our design variable. And just look with our cantilever beam, we're going to determine what can be changed and create the design variable that that defines what can be changed. So the R in Drco is response. So the next thing we're going to do is we're going to create a bunch of responses. Responses are our taking and reviewing important aspects of the analysis, be it a stress value, a mass, a volume, a displacement, a frequency, all of those types of things that we look at in an analysis. But in this case, we're going to be studying them and keeping track of them because they're going to be used to either limit how far the optimization can go, or in the case of the objective, to define our ultimate goal here. The C in Drco is constraint. These are limits placed upon a response. If we are pulling a response, if we are asking for information about the analysis, there are only two reasons why we would care about a response. One, we're going to constrain it. We're going to put a limit on it. I don't want my stress to exceed 200 megapascals. I don't want this displacement to be more than 3 millimeters in the y direction. I don't want this frequency to be above 1,000 hertz, or more likely, I don't want this frequency to be below 100 hertz. Those are all constraints. So that's a limit placed upon a response. So constraints are limiting the response. O is your objective, the last thing that we define. We take and we constrain every single one of the responses except for one. And that last constraint becomes our objective. Typically, it's going to be, for the most part, the vast majority of, or at least the majority of optimizations, the objective is to minimize the mass. So our response is mass, and the objective is to minimize it. You also have the option to maximize things, not very widely used. We far more minimize an objective than we do maximize an objective. So every single response, all of them but one, is going to be constrained, and that last remaining one becomes our objective. If you're not constraining or setting an objective on a response, then you get rid of that response. You shouldn't be studying it. That information is useless to the optimization. Important, maybe very important to you, but it's useless to the optimization unless you're limiting it with a constraint or setting it as an objective. Okay, so that's it for the boring slide presentation. I will probably come back to some here a little bit later when we get into specifics. But what I want to do now is I want to focus entirely on providing a demonstration as to how we're going to go about doing this sort of optimization. So what we have here is this little C clip. And actually, before we do that, let me just take a look here. Make sure. I believe Ricardo had mentioned you can ask questions at any point in time, so please do not hesitate to put questions in there. I'll try to keep an eye on them to answer anything that comes up. I think we have, yeah. So don't hesitate to ask a question. I'd be more than happy to address that. Okay, so I want to optimize this clip here. So I brought in this clip, and let me come here and shade that. So we have this little clip, and this has been set up for an analysis. Now, in the previous session, we talked about how to bring in geometry, how to create 2D and 3D meshes, and how to set up an analysis, creating constraints and loads. So we're just going to assume, as in this case, that those have already been done. We're not going to waste time going through that. You can see that I've got my part here. If I come to my model and my components, these are shells. They have been given a thickness. Where's my thickness? Oh, that's in the property. There it is right there. A thickness of 1, presumably millimeter. We've got a material defined in here. In this case, it's steel, a mat 1 with these parameters in there. Whoever did this also went through and set up the constraints. So I've got 1, 2, 3 different constraints here. This, aside from the rotations that they've gone with a simple 3-point constraining scheme, where they've limited all 3 degrees of freedom at this node right here. And then constrained in the Z direction to prevent rotation around that. So it left to its own, I could rotate around that point there, but the 3 prevents this part from rotating along the X, or around the X-axis, so that eliminates that. And then the 2 in this case, which is the Y direction, is going to prevent rotation like this. So this part is constrained fully with a minimum constraint scheme. And then we put a load in. So I've got 2 forces on these nodes right here. It looks like one is pushing out like that, and the other is pushing down like that, of 1,000 newtons in each load. So this part is set up for analysis, and it's important that it be ready to analyze. And that's because I can't do an optimization on a part that won't analyze. So typically what people will do is, once they have it set up, they'll just run a quick analysis on this. So I'm going to come here and you know what, let me save this as a different name, just so it doesn't overwrite what's in there. Just put my initials on there, and say OptiStruct. And so once I click OptiStruct, shortly, there we are, the run window comes up. And it looks like we are good. Analysis complete. So I could go through and take a look at the results. I really don't care what the results are. I was doing this more so just to make sure that I didn't make any mistakes. And you always want to do that. You want to make sure that your part is properly set up for analysis and the analysis runs. Because if you're going to be debugging your optimization, you want to be debugging the optimization portions of it, not the analysis portions of it. So make sure that your analysis runs before you do an optimization. So what I'm going to do now is prepare my optimization. And if we come here to optimize, you will see that we have all of the things that we can define for an optimization. And they've set it up following that DRCO. So you'll see all of these design variables here. We're going to do a topology optimization. And then you come down here, you'll see response constraint objective. So DRCO. RCO. Now, you'll notice I have a whole bunch of design variables, but responses, constraints, and objective, I only have one option there. Interestingly enough, when it comes to optimization, the only difference between all of our different type of optimization styles is just the definition of the design variable. What do I want to change? That's going to dictate the type of optimization. We're going to do a topology optimization. Topology optimization is this. This is my design space. The maximum amount of material that I can have, you're looking at right here. Think of it as sculpting. If an artist is going to carve a sculpture, they're going to start with a material, and that sculpture will never be larger than the block or sheet of material that they're starting with, because the sculptor is simply going to be removing material from that to reveal a sculpture. That's what our design space here is. It is all of these elements that define this part, and that means that my ultimately optimized part will not be any bigger than this right here. So my design space, my design variable, is going to be each one of these elements, and whether or not I'm going to include it in the design of my optimized part. So if I look at this element right here, do I need it or can it go away? Can this element go away? Can this element go away? That's what the optimization code is going to do. So my topology optimization, I click that, and I get this little flyout window here, and it says create design vars. I can call it, I'm just going to leave it design var 1. My configuration is topology, and it's asking me my property type. So what type of elements am I going to be running this topology optimization on? And these are shell elements, so I'm going to leave it on P shell. I have all these different choices here. The next one that we're going to do is going to be a P solid, but this is P shell. And we pick our elements not by picking the elements, but actually by picking the property that is assigned to the elements. So I click here and select my shell property and click OK. And now all of the elements that are in that, or that utilize that property, are going to be part of my my design space. So I'm done. I'm going to close that. If I come back to my model here, you'll see I now have my design variable. So D is done. And what's the next thing we do? Our response. So I'm going to come over here to responses. And it opens up this right here. And in this case, I'm actually going to change the name. And I'm going to call this volfrac. So volfrac is short for volume fraction. What that means is the fractional value of the volume of the part, right, the current volume of the part as the optimization goes on, as a fraction of the original volume of the part. So it's basically telling me how much material has been gotten rid of. It's actually telling me how much material remains, but subtracting that from 1, I get how much volume, or 100 if we're talking percentage, how much material has been removed, how much volume has been removed. So now I've named it. It's got an ID of 1. I have to come to my response type. What am I going to be taking response of? And as the name of it implies, it's volume fraction. So I'm going to come down here and volume frac right there. And then I'm going to leave everything else the same. It's going to be total. So all of the property by entity by sum, I'm going to leave it as total. So what this is going to do is it's going to continually keep track of how much of the volume of this part remains after it's getting rid of elements. Okay, so that's response 1. I'm also going to create another response. And in this case, the response is going to be a measurement of how far this node is moving. So with my design here, it's constrained. These forces are going to push on here. I want to come up with an optimized design that limits the movement of this node within a certain value. So to be able to tell it, I don't want that node to move further than something, some value, I need to set up a response. In this case, the response is going to be a display. Oops. Okay, don't know what that was. Displacement. So displacement of node A, and we'll say in the Y direction. You can call it whatever you want. And my response type is going to be, you guessed it, displacement, but it's not just displacement, it's called static displacement. I'm going to grab that right there. Now, unlike the Volfrac, where I didn't have to do anything else, I have to somehow tell it what I'm taking the displacement of. This is node A right there, so I'm going to come here, and I'm going to pick that node right there, click the little checkbox, and now I'm tracing that node. So it is going to determine the displacement of that node. But I have to tell it what direction I want that displacement tracked. And I'm going to pick DOF2. So it's kind of important you understand your degrees of freedom. Every node has 6 degrees of freedom. DOF 1 through 3 are translational. DOF 4 through 6 are rotational. And in the case of translational rotational, 1, 2, 3, X, Y, Z. So for me to track the Y translational displacement of node A, I have to pick DOF2. Click close, and I'm going to create one more response here. This is going to be disp B Y. It too is going to be a static displacement. This node now is going to be node B. And again, I'm going to change this to DOF2. So now it's tracking the displacement of this node right here in the Y direction. And if we look at the come on, go away. Oh, there we go. If we look at our little triad here, you can see Y is in the direction of the force. So close. So now I've got my one design variable. I've got my optimization responses here. If I come to optimization, there we go. So my optimization responses, Volfrac, display or displacement A in Y, displacement B in Y. So D and R are complete, and now I need to come to my constraints. So I'm going to create a constraint. I'm going to call this one disp. Oh, I'll call it constraint disp A. So my constraint on this displacement of A, I'll call it in Y. Have to pick the load step. I have to pick the response. I'm going to pick my response. The response is going to be the displacement A response. And I have to tell it what load step, what analysis am I studying. I could have multiple load steps here. So I'm going to pick that load step, click OK. And now I have to tell it how far I want to limit it. So I'm going to say my lower bound, what the minimum amount, I'll say negative 0.7. And my upper bound will be positive 0.7. So this constraint will be constantly taking a look at the displacement of node A, and if it exceeds 0.7 in the positive y, or exceeds negative 0.7 in the negative y, it will consider that a constraint violation and will have to adjust my design space accordingly to accommodate that. And now I'll create the exact same thing. Come back here so you can see constraints. So I double click on that, it opens up my displacement or my optimization constraints. Pick another one. We'll call this Disp B Y. The naming is entirely up to you. In a lot of cases, if I'm just quickly running an optimization, I'll just leave it as OptiConstraint 1, OptiConstraint 2, whatever. But if I'm doing a lot of things, I'd like to give it some sort of name highlighting what it is, because it allows me to come back and find it real quick if I have to make changes to it. So this optimization response now is going to be, of course, my displacement B. I'm going to pick the one and only load step I have. And it's going to be the same lower bound of negative 0.7 and the same upper bound of 0.7, and click close. Okay, so I've got my responses. I have my constraints. I have my design space. The last thing I have is an objective. Objective is really simple. In this case, it's just going to be, I'll call it oops. Back here. Apparently I left it. There it is, objective. My name will be min volfrac. I define my objective to be a minimize, and I pick the response that I want to minimize, the last one that I have. So every single one of my responses is being accounted for. I've got my displacements constrained. I have my volfrac constrained. And it's ready to run. So I just come here to optimize and click OptiStruct. And it will begin the optimization. Now, I don't know how long this is going to run for. We'll kind of keep an eye on it. You see it's got a warning here, topology optimization without minimum member size control. It'll run, but it's complaining about something. And you'll see what it's complaining about shortly. You can see it's taken a lot of iterations here. It's converging. And finally, it says, optimization has converged. Feasible design, all constraints satisfied. Perfect. This means that it has converged on an answer, and that answer meets all of our constraints, so it will work based upon the specifications that we set forth. So I'm going to come to my page 2 here, which I have as a hyperview page. Sorry, page 1 is my hyperview page. There we go. I'm going to come here to open. And if I go to my optimization directory, which is webinar folder, and I'm going to come down here and I'm going to look for, there it is, the design H3D. Double click on that, click apply, and I can see my part right here. So now what I need to do is I need to come here to my contour, and you see the only thing I can contour is element densities. Density is how the optimization is going to work. What it is doing is it's altering the density of each element. But when I say density, do not think of what you're thinking of, which is the density, how you determine mass by the density and volume. Think of it instead of the density of importance of the part or of the element. What actually is happening is it's assigning a density volume to that, which not only affects the mass of that individual element, but it also affects the strength of that element. So you can think of it on a scale from 0 to 1. An element with a density of 0, the optimization codes have determined that that element is entirely unnecessary. And if it has a density of 1, it's 100% necessary. So it takes that value, it multiplies it by multiplies the Young's modulus by that value, and that's how it determines the importance of that element. And that tells me what elements are important and what aren't. So I'm going to come here and I'm going to contour this. So element densities, I'm going to click apply. And you see right now, everything is the same. And that's because I'm on iteration 0 of frame 25. If I look through here, all of these, it comes all the way to iteration 27. If I select that, now I can see my part. This is what it ultimately converged on. I can actually even animate it, but I do have to change this to a transient animation so it runs through each one of the iterations, and I can see how it is converging on that design. Let me slow that down just a touch. So you can see it's eliminating parts. So blue means 100, it's absolutely not necessary. Red means it's absolutely necessary. And everything in between as a cutoff limit. Now, I had asked you to remember that warning that we got. You'll notice here that this part isn't really very discrete. I can see kind of a member forming here, but the rest of this, I've got things that are absolutely important next to things that are not important at all, next to things that are kind of medium-high important, next to things that are medium-low important. This is what we refer to as checkerboarding. Look at it, and it's kind of obvious as to why we call it checkerboarding. This happens when you don't define a value called the min-dim. And I intentionally left that value undefined because you need to see this so that if you encounter this situation when you're running optimizations, you understand why. If I come back to my part here, and I come back to my design variable, you will see down here a value min-dim. That's what the complaint was from the solver, that I didn't define min-dim. Min-dim is what is the minimum dimension of any member that it creates. And you can think of the members as, give it a second to catch up, these things right here. This is a member. This is important elements, and in this case, these elements are about 2.5 millimeters. So this would be, 2.5 squared plus 2.5 squared, the square root of Pythagorean's theorem. So that would be the width of this. We'll just say it's 2.5, which is pretty small. What I'm going to do is I'm going to come here and I'm going to change my design variable so that it includes a min-dim of 7. Now, any element or any dimension that's created can't be less than 7 millimeters across. I can also set a max dim, not widely used, but if you have a situation where you're planning on casting the part or doing like a injection molding, you may want to set a max dim so you don't get big blocky parts which end up being difficult to create with casting or injection molding, because there's a maximum to how thick something can be when it relies on cooling from a molten state. Okay, so now that I've defined that, all I did is I defined min-dim. I'm going to run the optimization again. We'll run it live, and I'll call this EWL, and we'll rename it dash min-dim, and we'll run it again because it will happen pretty quickly. We won't get that warning again. You see no warning this time because we did what we were supposed to do. And it should happen pretty quickly, and we will take a look at what happens now with the min-dim, because I think we're going to be much more pleased with the part as it is. Looks like it's taking a few more iterations. Anytime we do things like this, it will take a little bit longer. Every constraint, every limit you put on there, it can take longer. But it says optimization is confirmed, and it is a feasible design. All the constraints are satisfied. So I'm going to pop back over to my hyper view. I think what I'm actually going to do is I'm going to split my screen in half here. There we go. And I'm going to come here, and I'm going to open up my min-dim results in this, because now we can compare them side by side. So I'm looking for that H3D, the DES one. That's just short for design variable. So min-dim DES H3D. Click apply. Looks like that. I'm going to come and change to my final iteration. This one is 48 as opposed to 27, which is what it was before. Come to my contour, come to element densities, and apply, and look at that. Now you can see the difference between going with min-dim and going without. This part is very, very well defined. We can kind of see the general direction it was going in here, but now this has defined it. And to get an even better idea of my part, I can come here to the button next to contour, which is ISO, for isolate. I'm going to ISO element density, simple averaging. I'm going to click apply. And I'll come over here and click apply. And what this allows me to do is specify a cutoff range for density. I will make it 0.38. And now we can see this is what our part should look like. To minimize the volume of the part, but maintain the requirements that we specified. And to verify that, I'm actually going to add another window here. So I'll come to 3. I'm going to come to File, Open, Model. And I'm going to come back to my min-dim, but as opposed to the des.h3d, I'm going to pick the s1.h3d, click Apply. You'll see this one just has the 0 and has the 48. So I'm going to pick my 48 frame here. I'm going to click Contour, Displacement, Apply. And if I now come here and take a look, you can see that my displacement on that node right there, which one is it here? What's this? Salt type displacement. No, that's not it. It's the there we go. Nodes. No, that's not what I'm looking for. I am looking for notes. Nope, that's not notes. Yeah, I guess I can put a note there. I'll attach it to an entity. And nope, entity, there we go. Oh, I have to add a note. There we go. Add a note. We'll attach it to an entity. We'll pick that node right there. And the field name will be entity contour value. Insert that field. And apply. And you can see 0.7169. So right about at where we were at with our requirements. So that's kind of the basics of topological optimization. What I'm going to do, let me check the questions window here. I'm going to pause here for a minute. We're going to move on to a little bit more complex optimization using 3D elements. But before we move on to that, I just want to ask, are there any questions that anyone has about kind of the basics of optimization, the DRCO approach, what each of them means, how we go about doing an optimization, anything along those lines? Okay, let me also show you something here. So one thing that we can't do with this file where we actually see results is we can't see the shape of the part because I don't have a way of contouring both the results and the element density, but a nifty little way of still being able to see my results, so I can even come here and contour my stresses. You'll see my stresses are solely on the shape of the part. By taking, because it altered the densities of these elements, they don't, and they become essentially non-structural elements, they don't get stress on them. So if I, even if I'm contouring displacement, if I come here to my ISO and contour, use my stress as an ISO and click apply, all I have to do is move it just a little bit off of the 0 point, and I can see the shape of my part. I can animate it. So that's the basics of optimization. Okay, so let me stop this, pause it. Oh, little tip here. With the result one, don't forget to change it from iteration 0 to iteration, the last iteration, in this case 48. And many people, when I've taught this class live, who take a look at things and seeing, oh my gosh, my results don't match, or they're not what I'm seeing. I'm not seeing any results. Make sure you go to the last iteration. Okay, so let us shake things up a little bit. Let's make things a little bit more complex. And we're going to do a slightly more complex optimization here. And this optimization is going to be on a 3D meshed part. This is going to be a control arm. New. No, I don't want to save. Yes, I know it's going to discard, blah, 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 blah. So now I'm going to come here. I'm going to say File, Import Solver Deck. And I'm going to come to 3C and let's import this right here. Okay. Oh, actually, I think I grabbed the wrong file. I didn't want to go into that directory. File. I don't want to save it. Okay. Oh, wow, and I just completely killed Hypermesh. That's fine. Give it a second to reboot. There we go. Okay, now we're back in business. Okay, so let me come back to here. File. Well, gotta finish loading all this stuff. File. Import. Solver deck. Desktop. Webinar folder, and we're going to grab control arm.fem. This is the one that I want. Okay. So now let me come to my components here, and we're going to make that shaded, and we're going to make that shaded, and we're going to make that shaded, and let us now begin this one. So what I have here is I have a control arm. You can see I've got 3 different components. So this is going to be my design space and my non-design space, and then they went and created a separate component for RBEs. My rigid beam elements, always good practice. So this big pinkish looking chunk here, that is all going to be my design space. These mounts here are non-designed because this is where it attaches to the vehicle and the wheel here. And then they put this little guy in here because of the jounce bumper. So that's where it has to have a positive stop right there. So anything in pink can be gotten rid of. I'm not going to bother running the analysis on this. I know it works, but always remember when you're setting this up on your own, the very first thing you should probably do is run a quick analysis on it to guarantee that the part runs. So what we want to do is we want to run an optimization on this. So if we take a look at our part, we've got those 3 components. We've got 3 load steps, subcases. They are corner, brake, and pothole. So this has 3 different scenarios that are important to this design. So what are the stresses on this when it's cornering, or displacements on it when it's cornering? What is the effect of a braking load on this as the vehicle is braking, and what's the effect of a pothole on this? And it's important that we have all of these loads and all of these different load steps, because we need to run an optimization that takes all of those into account. So we have to have all of them in our model. So any scenario that's important to your design, make sure you have each one of them defined in your model. And that will guarantee that you get an optimization that takes all of those into account. So we're going to come down here to optimize. We're going to do a topology optimization. DRCO, design space first, topology. Just going to call this, we'll just leave it as design variable 1. I'm perfectly happy with that name. It's a topology optimization. This is no longer a P shell, though. It is a P solid. because I'm creating I'm doing an optimization on solid elements, not shell elements. If I were to leave it as P shell, I could set everything up, and as soon as I went and ran it, I'd get some nasty errors coming out of OptiStruct saying that an inappropriate element type or no element type found or something along those lines, because it would be trying to tell it to optimize shell elements, but there aren't any. So make sure you change it to whatever type of element you've got. Now, of course, just like with the shell elements, I have to pick the property. So I can come and I can pick it on the screen, or I can pick it from here. I pick my design, I click OK, and now the property is there. I'm going to leave min-dim empty. Min-dim isn't as important when you're doing solid optimization. It's really critical when you're doing shell optimization. But in a lot of cases, what I'm going to do is I'm going to leave as many restrictions off on my first run as possible just to see what comes out the other end. And then I'll add restrictions to it as necessary. And I don't think a min-dim's necessary, so I'm just going to kind of leave it. So that we're kind of good with what we've got here. Click close. Let me just check my design variable. Sure enough, there's my design variable. I can always click on it and come and pick here. We're not going to do it, but we do have the option of doing a lattice optimization. What a lattice optimization will do is replace a lot of those less dense regions with a lattice. It's a really slick way of running an optimization. 100% guarantees that you have to 3D print the part. We can't create lattice in any other way than 3D printing. But it's an option that you have. If you Google Altair lattice optimization, you'll see some pretty cool designs that were developed with our awesome lattice optimization. Okay, so that's done. Next thing I would need to do is create my response. So I'm going to come here and create a response, and I'm going to call this here volume. Oops, why is it not? There we go. Volume. And the type of response is going to be the volume of the part. This is not volume fraction, so I'm not keeping track of the fractional volume. I'm keeping track of the actual volume. And it's going to be total. Check my optimization constraints, volume. I'm going to create responses. I'm going to create another response. This is going to be a static displacement response. So this is going to be displacement, going to be static displacement, and I'm going to pick that node right there, node number 1. And the direction that I want this to go into is total displacement. So I'm going to not take a look at it in a specific direction. I'm going to do total displacement because I'm going to create 3 different constraints for this. But oh, wait a second. No, my mistake. Hold on. No. Yeah, we'll leave it at total displacement. That's fine. And close. Okay, so now I get displacement. What I'm actually going to do is use this response 3 times, though, because I'm going to create a constraint for each one of the different load cases that have a different limit for displacement. So now I'm going to come here to my constraints, and I'm going to call this disp corner. I'm going to pick my displacement response. Oops, why didn't it? Okay. Displacement response. There we go. What doesn't it like about that? Corner. Displacement. Okay. And now I'm going to pick my load step. Okay, what doesn't it like? Displacement. Okay. Says DRE report generation is already turned on. Select another response or turn DRE report for this. Okay, what the heck did I? Oh, that's why. I clicked this accidentally. I did not mean to click that. That was silly. Okay, that's why I was complaining. So now I come back here, and this constraint will be disp corner. To pick the displacement, click OK. There we go. Now it likes that. And the load step will be, of course, the corner load step. And in this case, I'm just going to do an upper bound, and my upper bound is going to be 0.02. I'm going to create another constraint. This one's going to be called disp break. I can reuse that response. Remember, the response is just pulling information from the analysis. I can use that as many times as I want. I don't have to create a separate response for each one of these constraints. And this one's going to be 0.05. And last but not least, we're going to create the disp hole. And the response will again be the displacement response, getting a lot of mileage out of that response. Pick the pothole, load step, set an upper bound of 0.04. Okay, D done, R done, C done. What's left? Objective. Click my objective. Objective is fine. We're going to minimize, and what are we going to minimize? The only thing we have left to choose from, the volume, and click OK and close. And that's going to give us an optimization. Now I can come here and I can run optimization on this. Actually not. This one does take a little while to run. So as opposed to just sitting and watching it grind through, I'm going to cheat and do the baking show routine where they mix the batter and pour the cake and they make everything look great, and then they slide it into a fake oven and go turn to their right and pull out an oven or pull out a cake out of the other oven. So I'm going to come here and I'm going to open C, simple optimization, grab this and click apply. Again, it doesn't look like anything happened. I can come and contour my element densities, click apply. It's going to say my non-designs are 100% necessary. My design space is 0% necessary. And that reason is because I need to come all the way down to iteration 26. And now all of a sudden, I can see my part. Even more importantly, with a solid part is the ISO. I'm going to come here to my ISO. I'm going to click apply, and we can kind of see what's going on here. So we end up with an interesting part. It works, but this kind of jumbled mess here, well, it's a great optimized design. It's not something I could really manufacture in a traditional sense. There's no way I could create this without either doing some crazy difficult machining or run it as a 3D print, which for an automotive part is pretty much impossible. There's no way that 3D printing can keep up with the production volume of automotive. So the part that I ended up with isn't really useful to me. And now what we need to do is address the concept or the idea of manufacturing constraints. So we'll talk about constraints, but no longer are we talking our optimization constraints. These are actually manufacturing constraints. So restrictions set upon the part or the optimization based upon the requirements for manufacture. And I did say I would potentially come back to my slides here. Let me see if I can find these. Oh, just here's some good slides talking about member size. So you can see that checkerboarding here. Member size helps out there. There is another type of constraint we can put on there is symmetry. Symmetry guarantees we get symmetrical parts about 1, 2, or 3 planes. But what I want to talk about are manufacturing constraints. Single draw and split draw. These are used when the part is going to be manufactured by metal stamping or by casting. And you can see kind of from the picture there what that means. And that means that we're going to be coming at this part, designing this part, or manufacturing this part from a specific direction. And this design will guarantee that we don't end up with things like this. Holes that run through the side, parts that are undercut, carved out areas, little caverns inside of it. All of these are non-manufacturable when we have a tool coming from one direction, be it a stamping or a casting. We can't manufacture it in that direction. Split draw does close to the same thing, but it allows it to come from 2 different directions here, but everything has to be going in those directions. And you can see in this case, if with this part right here, if I don't use a draw direction, I end up with a hollow cavity. Whereas if I force a draw direction, I end up with ribs, and I kind of get this cross-hatched pattern with ribs. This is another control arm here without draw direction. Again, you'll see a lot of these hollow designs. Hollow designs are quite popular without draw direction. With draw direction, we get a nice defined member that runs across it. that guarantees that the part is manufacturable. And we can also indicate stamping, where it will try to make it a thin, constant thickness, and hole or no hole. So we can you'll see a lot of times with these design constraints, we'll end up with holes going through the part. If you specify the no hole option, it will prevent holes from being created. So the manufacturing constraints really help us optimize a part, because the best, most incredibly optimized part that's ever existed, weighs next to nothing, is as strong as anything, is completely useless to us if we can't manufacture it. So manufacturing constraints are very important to us. Fortunately, they're also surprisingly easy to create. And so we're going to make a slight adjustment to our part here. So we can kind of pick up where we left off from with this part right here. So what I'm going to do is I'm going to come back to my design variable. And if I open this up and take a look down here, this is where we can define our manufacturing constraints. I have my draw direction here. So I'm going to say I want a single draw direction. And then I have to pick two nodes. So what direction do I want this to be? So in the case of this one, I'm going to pick my anchor node as node number 2. And what's called the first node as node number, which one did I pick? You know what? I may have been looking at that bad. Okay, that's fine. Good. I wanted to make sure that I wasn't having like a little parallax effect here. Node number 3, perfect. Okay, so let me bring this back over here just so you can kind of get an idea. So my anchor node and my first node, so that provides the direction that the cavity will be oriented to. Now, the next thing that I need to do is create a right here, not draw, pattern grouping. I have 1, 2, and 3 plane symmetry. I also have cyclic symmetry, but I'm going to do a 1-plane symmetry. What that will do is it will create one plane that the part will be symmetrical against. And in this case, my anchor node will be node 2 again. That's going to provide the location of the symmetry. So think of it as a mirror being built with that point included with it. And my second node provides the normal to that mirror. So I'll pick this node right here. Pick any node along here. It doesn't matter. It means that my mirror plane is going to be through that node, normal to the vector created between these two nodes. And that means that my part will be symmetrical on both sides. So now I have my direction, my draw direction. I have my normal plane. And now when I run my optimization, what I'm going to get is a part that will meet the manufacturing requirements that have been set out for it. Again, I'm not going to run the optimization because it will take a fair amount of time. So I'm going to cheat again, and I'm going to come here, and let me come to my hyperview window here. Let me split it again so we can kind of compare what we ended up with. It's kind of a little bit of a jumbled mess there. But let me come to this side, and I'll say File, Open, Model. And I will now come to here and come to my draw. We'll grab my Des 3D, H3D. Take a look at my contour for my element densities. Hopefully. What the heck, why is it not? There we go. Okay. Element densities, click apply. So now you can see drastically different, but again, with the solid parts, we absolutely have to come here to ISO, click apply. We'll come down here to about there, and now you can see the results of that. So we can see the comparison between the two. Let me maximize this window here. There we go, and come here, and we'll turn it back to just one window so we can see. There we go. So now you see the results of that optimization with the design constraint or with the manufacturing constraints. It's kept my non-design spaces. You see it even built up a little region in here to accommodate for that. The part is absolutely symmetrical across that plane of symmetry there, and it can be manufactured the way that I want it to be. If I were to come back here, you see how there's a big hole in here. If I were to come back here and remember the hole, no hole here. There we go. If I come back to my design variable and select this and come down and pick no hole, if I hover over it, says prevents the formation of through holes in the draw direction. Note it does not prevent holes perpendicular to the draw direction. The assumed maximum thickness of the draw direction is twice the average mesh size. So what it would do, if I were to select that and then run the optimization, I would not end up with this big hole here. It would kind of fill that in. I can kind of get an idea of what that would be. You see how